Hi guys, Shouvik here. Welcome back to YouTube channel. So today we will continue the same things of our 100 days of 2026 coding challenge that we have started over yesterday, and we will solve the today's problems of the Leetcode daily challenges that we have. Yeah, so let's get started on this particular problem. Yeah, so on today's problems we have maximum product of splitted binary tree. Okay, so let's read out the problem statement first. So given the root of the binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sums of the subtrees is maximized. Clear, right? I think the problem statement is very clear on the first read itself. So they have given us the root of the binary tree, and we have to split the binary tree into two subtrees by removing one edge. So if we are going to remove one of the edge from the tree, then it is gonna be divided into two subtrees. So for example, if we remove, so this is a binary tree, right? So if we are gonna remove this particular edge, which is highlighted as red, if we are gonna remove this particular edge from the binary tree, it is gonna divide it into two subtrees, one holding 2, 4, 5, another holding 1, 3, 6. Now what they are asking for, they are asking after removing one such edge, you have two subtrees. Now you have to return the maximum multiplication value. In whom the maximum multiplication value of all the node sum of the left subtree multiplied by all the node value sum of all the node value of my right subtree. We have to return the multiplication of all the node value sum from the left subtree, and same for the right subtree. The same all the node sum of the right subtree. So let's suppose from left subtree we got the sum as x, from right subtree we got the sum as y. We have to return x cross y in such a way that x cross y should be maximized, because we can divide, we can remove this particular edge, or we can remove this particular edge, right? Based on that, the left subtree sum and the right subtree sum is going to be different. So the multiplication value x cross y is also going to be different. So out of them all the possible scenarios of removing the edge and creating two binary trees, two subtrees, we have to return the max of those. We have to return in which partition it is giving max x cross y value that we have to return. The same things they have mentioned. Return the maximum product of the sum of the two subtrees. Since the answer may be too large, return it modulo 10 raised to the power 9 plus 7. There is no super magic on this line. Note that you need to maximize the answer before taking the mod, not after taking it. So that is a small point that you have to remember for sure, that you have to do the mod after you have maximized your answer, not key on the runtime. When you are maximize your answer, you are taking the mod and then you are maximize the answer. No, that is not the case. We first have to maximize the answer, whatever the maximum value you can achieve, and finally before returning your answer, the maximum answer that you have achieved, you can just do a modulo. So for this example test case, you can see this particular divisions give you left subtree sum as 11, right subtree sum as 10, and 11 cross 10 is 110. That is the maximum you can achieve for this particular binary tree. If you are gonna remove this particular edge, then this is my left subtree and this is my right subtree. Left subtree sum is 6, right subtree sum is 15. 15 plus 6 is 90. That is the maximum you can achieve. Correct? So I think the problem statement is very clear on the first go if you read it thoroughly. Now quickly jump on the intuitions part. So on the intuitions part, let me find my marker and let me check on the recordings. Yes, it is working fine. Okay, so if I am gonna draw a binary tree, it's too huge. Why it is too huge? Opacity is fine. Opacity I can decrease. Okay, it's gonna decrease my opacity. Okay, so what I am trying to say, that if you have the binary tree, let's suppose this, how actually we have to think on the intuitions, how actually we have to build an algo over there. So also let's just quickly take a look of our constant. So our constant is as big as 5 into 10 raised to the power 5. So the maximum our algo should be big of n, or n log n is gonna accept it, but not something kind of n square is gonna accept it, right? Based on the constant. Clear? So So what I am trying to say, so what actually are you guys able to see some options? Do we have some options? Yes, Shouvik, yes, we have definitely have an option here. What is the options? I can split this particular edge, then my left subtree is gonna be this, and my right subtree is gonna be this. What are other split possible? If I am gonna split this particular things, if I am gonna split it from here, let's suppose I am gonna split it from here, then my left subtree is gonna be which one? Tell me guys. This particular subtree, and my right subtree is gonna be this particular subtree, right? Like this way, for every edge, we definitely have to try to remove this particular edge and take the sum after removing that edge. If we are able to consider the sum after removing that edge, what are the child subtree, what is the current subtree sum on the child node. So what do I mean by child node? So let's suppose I am gonna remove this particular edge. So on the left part, after removing this particular edge, this is my left subtree. If I am tracking the sum, if I am tracking the running sum of a particular subtree, if I am gonna making the running sum of my of any of my subtree, so can I compute what is the sum of my right subtree? Yes. So my algo should be how, if I have my, let's suppose, left subtree sum that I am computing in runtime, and if I have that value, can I compute my right subtree sum? Can I compute? Yes. What it is? It is nothing but my total sum minus my left subtree sum. As simple as that. Agree guys? Totally agree on this. Now the question is, how I can calculate my total sum? Is it not super easy? I think yes. It's definitely gonna be super easy. You can do any traversal on your interest. You can just do a tree traversal. It can be DFS, it can be level order traversal, it can be depth first search or breadth first search. It can be either BFS or DFS, and you can do either of them, level order traversal or DFS. You are gonna do the entire my subtree sum. You are gonna do the entire tree sum is equals to my total sum. So on the first iteration, so if I am gonna write the steps, how actually we have to build the intuition. My first step should be do any traversal and stores the total sum. That is my first steps. That should be my first steps. Do any traversal and store the total sum. Agree? Totally agree guys. What is the next step? On next step, when we are calculating how actually we can calculate my left subtree sum. How actually we can calculate my left subtree sum? Will not this also be a super easy? So how actually we can do? If you are following our last videos, then you will definitely know. So for every subtree, when I am at this node, I am gonna be return what is my left subtree sum, what is my right subtree sum, plus what is the current value. That is, I am gonna return on every DFS call. I am gonna do DFS. From there I am call its left, and from its left, if it is going to point to the none, if there is no node, then it is gonna return a 0. So the left subtree sum is 0, and for this the right subtree sum is also, it's a none, it is gonna return also a 0. Now from this node, what is the value? It is populating to its parent. Left subtree sum, that is 0, right subtree sum, that is 0, plus the current node value. What is the node value? That I am gonna return from this particular DFS call. Very simple, that we are doing from last 1 year over that particular things. That is how DFS is actually work. So when the call actually come at here, this particular left subtree call that we made from this particular node. So if I can redraw, so when I am making this left subtree call, this particular call return back me the entire tree present, including this particular node to this parent node. Similarly, I will make a call and get all entire subtree present. That can be any black box, and it is gonna return me the entire right subtree sum to including this particular node and its successive all the nodes. And I am basically going to calculate when I am at particular this node, I have my left subtree, I have my right subtree, I have my current node. So including this particular node, my entire subtree, including that particular node, the value should be my left sum plus my right sum plus current node value. And if this particular node is gonna attach with some of its parent node, and if I am gonna remove it, then what is my one of the subtree sum? Is nothing but this. So maybe I can consider it as a left subtree sum, or maybe my first subtree sum. And what is my then next subtree sum? Is nothing but my total sum minus this. Agree? Totally agree. And that is the game we have to play here. So guys, if you are not able to understand any of the part of this particular intuitions, I will definitely suggest you to reiterate this particular part, because that is the gist of this particular problem. Once you get this, then writing the code is a cakewalk for you, for sure. So now we'll quickly do the code iterations. So on code iterations, I have written two helper functions. The first one is for the total sum calculations. So I have created two class level variables. One is self of answer and another one is self of total sum, right? Two class level variables. And I am calling my helper one with root. And if my root is none, then return 0. So there is nothing to return. And my left sum, how I am going to get it? Call your helper one recursively to root.left. What is my right sum? Call your helper one recursively with root.right. And what is the total value you got? From left sum plus right sum, including that particular node, is nothing but my left sum plus right sum plus root val, right? That is the entire subtree sum, including the current node on which we got the call from the root. That sum is gonna be returned from my helper one. And like this way, when it is going to explore all the nodes, it's gonna return its left plus right plus node val recursively, and my total sum is going to be enriched with a total sum value. Very simple. And same DFS code we have to write one for helper 2, and this helper 1 is for total sum calculations and helper 2 is for our answer calculations. So which value we have to call? We are going to invoke our helper 2 also with root as it is. There is no game change. If root is none, return 0. If otherwise, if my root is not none, if the root has some value, then get the value of its left sum. Yes, we will get helper 2 call with root.left. Call its right subtree with helper 2 of root.right. We will get the right sum. What is the current tree sum then? My left current tree sum is nothing but the current subtree that we are gonna consider currently. It's gonna be my left sum plus right sum plus root val. So that is my one of the subtree part, and that is my one of the subtree part. And what is the opposite tree sum? So if we are gonna split that particular edge, if you remember that we have just discussed, if we are gonna remove this particular edge that we have just discussed, then what is my left subtree, or what is my current subtree sum that we have already calculated? Left sum plus right sum plus node val. What is the opposite tree sum? Is nothing but my total sum minus this current tree sum. Exactly that is. Opposite tree sum is nothing but my self of total sum minus current tree sum. And then try to maximize your answer with the current current split. So for every split we will try. We don't know which of the split is going to give my optimal answer, right? Which of the split is gonna give us the optimal answer that we don't know. So that's the reason we will try to break on every branch, every edge we are trying to break and trying to maximize our answer So our self of answer is gonna be maximized with my current self dot answer with current tree sum into opposite tree sum. So how we will get the current tree sum and opposite tree sum? By removing the edge from the current node to its parent. So we have removed that node, we have removed that edge, and we got two subtree, and we have current tree sum. We calculated the opposite tree sum by negating it out from the total sum, and we are trying to maximize our answer. So for every node, we are breaking that edge to its parent. And we are trying to maximize it. Like this way, my self of answer is going to be always optimally calculate the maximum sum possible by trying all the combinations, all the removals of each of the edge, and it is keep on trying for every edge of the sum. And finally, we have to return our answer with self of answer with a modulo of 10 raised to the power 9 plus 7. That's it, guys. Now if we can quickly discuss the time complexity. if we can quickly discuss the TC, tell me guys what it is. It should be big O of 2n, because we are going to visit every node twice, once by helper 1 and another one is by helper 2. And what is the space complexity? If I am not considering any recursive stack space, then it is gonna be of big O of 1, I guess. Yes, we are not using any extra space, right? If I am not going to consider the recursive stack space, then it is gonna be a big O of 1. And if you are going to consider, then you can tell, if we are going to consider the recursive stack space, then it is gonna be of big O of how much? Big O of n. So if I am going to show the memory what it is showing us, big O of h. So that is the height of the tree. So height of the tree is nothing but the maximum recursive stack space that we can achieve, because the DFS is gonna be depth. It is gonna be depth of the maximum height of the binary tree we have. It is gonna be doing the DFS. The DFS is gonna be go to the extreme depth by storing all the nodes in the recursive stack space. If you are going to basically consider those particular space, recursive stack space, this is, then that is gonna be take off big O of h. That you can explicitly tell to the interviewer. And on runtime, it is definitely gonna be big O of n for sure. So it is actually big O of 2n, but on big O notations is kind of a big O of n. So yes guys, that's all on this particular video. And if you find this video helpful, so please share the videos to your friend circle, and please consider to subscribe to our channel, so that we can bring this super quality content to you guys for the upcoming days also. Okay guys, thank you. With that note, we can close the video. Thank you. Bye bye.